just to welcome you to the Majorana lectures. And it's a great pleasure and a great honor for just Professor Hooft that we Nobel Prize in 1999 for physics. And I thank him very much for having accepted to be with us in Majorana lectures, as well as for the next lecture of Antonio Barone, and I think they are scheduled for the next Wednesday, as you know. But let me say a few words. And the presence of Professor Hooft here is really, he has a special meaning for us. As our community of the identified section of Naples and the Department of Physics is very much involved in research of physics. And essentially as well on theoretical and experimental point of view, and also in astrophysical and nuclear physics. And I think that our community also provides a contribution to this year, to research and step forward in science. So for example, the discovery, the recent discovery in 2012 between AMS and the Atlas collaborations. And I think that this discovery really opened a very exciting season of research, in particular physical astroparticle physics, but I think also with connection with cosmology. And that it will face very important other questions in the near future, like, I think that even the subject of your seminars, like dark matter, neutrino physics, but also, the negligible adversity of electronic interactions, and maybe we have some inputs of essentially the new physics beyond the standard model. And I so think that our community is really working on that, but that is another thing important. There are some other questions that I like to mention. For example, the direct observation of gravitational waves. Let me remind you that this year we are celebrating the century of gravitation, general relativity. That's very important. And also, for example, the study of the stars, of the universe, the evolution of stars. All these, why I'm saying that? Because I think that all these studies, they, for perhaps a more extended framework, aim at studying the history and the evolution of our universe. And I see many complementarities between different communities, like not only particles, but nuclear particles. So I think that's, I would like to underline this. But coming to the conclusion, these Majorana lectures, and also your seminars that have a really important role in this framework. And I thank very much the petitions that for this initiative is one of the most important one in our IFN section and the department. They are very active this week. And let me conclude just saying that I am very glad to see many young students and researchers. I think this is a great opportunity for them. And I would like to tell them that they are lucky. They are lucky because they happen to work in a very exciting field of physics. And as in the near future, maybe we have some important answer from nature. This is our experiments and our theoretical work. So let me conclude just wishing good work and thank you again very much. Professor Hooft will be with us, and I hope you will enjoy staying in Naples to be with us in this week. And so I invite him to start his meditation seminars. And thank you very much again. Thank you.
Before we start, just one technical detail for the students of the Laurea Magistrale. There are the 2 credits for altre attività that we have to sign this. Then also doctor students who tell us that they are here. I'm glad that there are so many of you. Okay, I have to introduce the speaker, and when somebody comes very often, then the chairman says, okay, we all know such and such. It's the first time that Gerard comes here, but I can so say we all know his work. We don't know him, but we know his work, and the list is somewhere there. I wrote an organization of
much. So it's a great pleasure for me to be here and with lectures a name of a very famous Italian physicist, Majorana, who unfortunately deceased much too young. He left us. And physics has gone a long way since that time. So before I start, I have to say that I did not know exactly what kind of problem to expect, how large a percentage of the public are physicists who already know a lot about the Standard Model and or they can see some details or some new things, or others who still need to be introduced at a much more elementary level. So I started by assuming rather little in the audience, and then gradually, but soon enough, I'll go into much more technical detail. So I didn't really prepare to make combinatorial derivations. Also, this is the reason why I use the blackboard. If I do the right thing, I'll need some time writing it at the same time you can digest what I'm trying to do. So, yeah, I start with the Standard Model. The Standard Model is described by the Lagrangian. Somehow I'm trying to avoid so we have Lagrangian. So L is a symbol for Lagrangian, and L is and the abstract way of writing down the equation is that the Standard Model contains basically 3 parts. And it looks something like this. Yeah, that's not what it is.
Acrobatics
so, this expression, most of you know what it all means. If you don't, then you say it consists of 3 parts. This describes what we call the vector particles, which means that they have spin 1. And the general name is photons, but the technical name is Young-Mills particles. And these photons are required to be organized in a very mathematical way. The mathematics of group theory. And so there's group theory involved. Lie groups to be precise. And Lie group theory tells you that there is a particular Lie group called, which you might call G, and these vector particles must be arranged in accordance with that Lie group. Many of you do know the details, some of you might not know, but the Lie group that turns out to be relevant for the Standard Model is called SU3 cross SU2 cross U1. Now that's the mathematical name for a group which consists of 3 parts, SU3, SU2, U1, and together they form a group. And in principle, in physics, you could have used any other group. So it doesn't have to be SU3, there could be symplectic groups, there could be other orthogonal groups. In fact, this has a group SU5 which contains this whole thing as a sample. Maybe one day we'll have to replace this group by SU5, or even more generally SO10. Some people suspect that this is the underlying group theory structure of the Standard Model. This turns it into an orthogonal group, just like the group of the rotations in the Lorentz group, so that the Lorentz group is SO31. So space-time is in this way, and the interesting thing about that together form perhaps the group SO 13.1. So maybe there's something like this going on. We don't know, but the algebra of theory suggests perhaps this to be some sort of underlying group structure. Now that's all left for the future, but there is two other parts of the standard model you mentioned. These are basically what we call the matter particles. They are described by the Gerard equation, and they describe particles with spin on half. And the spin on half particles are typically the fermions, the electrons and the quarks of the theory. And the electrons and the quarks must again be chosen to reflect the same group structure. So in technical terms, they have to be representations of this group. And nature chose the representation to be 3 cross 2, 3 cross 1, and 1 cross 2 and 1 cross 1. So these are the quarks, and these are the leptons. And again, we could have chosen other representations of the same, it must be the same group, but the representations could have been chosen different. For some reason not yet understood, nature made this particular choice. And then finally there are scalar particles. Their spin 0, obeying the time-Gordon equation, but hidden in the mathematical notation is the fact that they interact primarily with these vector particles, and because they all interact with the same vector particles, indirectly they interact with each other. This is a more direct coupling between the spin 1/2 and the spin 0, called the Okada couplings. And again, there's many choices one can make. One can choose also the representation for the scalar field. They turn out to be only a representation of 2 plus 1 of the SU2 cross U1. The SU3 representation is trivial for some reason, and there's basically only one scalar field in nature that seems to be necessary for a standard model, and that is in particular the famous Higgs field. So the Higgs field is a spin 0 component. We need a spin 0 to generate this term, which corresponds to the masses of the matter particles. The quarks and fermions and electrons all carry mass, and they only do that because they are coupled to the Higgs particle. And is there identifying that, what was already mentioned, that a few years ago, finally, the particle associated with this sector has been detected. Very probably, all indications are that the particle detected at CERN is indeed this one missing link of the standard model. But before that, although we knew that this particle had to be added anyway, the particle associated with it, the Higgs particle itself, had not yet been detected. And it is also known that to detect this particle you need lots of energy, and you need machines which for a long time were out of reach, but finally the particle has been pinned down, and it seems that everything is okay. Well, that means that, okay, we understand how all known subatomic particles interact, we understand how to compute these things, but there's some things we don't understand. We don't understand why the group structure is chosen like this, why everything is organized in this particular way. But there's something else we don't understand, and that is that in this theory, hidden in this very condensed mathematical notation, is the fact that the interactions require some interaction parameters. And each of these elements of the group contain interaction parameter. Here it is, so it's G3, G2, and G1 are 3 elementary coupling constants that go with this theory, and they have certain values. G3 is very large, G2 and G1 are small parameters in the order comparable to the 5 structure constant in quantum mechanics. which means that the SU3 forces are very strong. The bigger these coefficients are, the stronger the interactions. The SU2 and U1 interactions are very weak. So, and they control the weak force and the motor force. So, and these forces are much weaker. Now, these are three real numbers that you can measure. And we now know these numbers. These you know very accurately, this one you know fairly accurately. And, but they have to come from measurements. We do not know what in nature causes these constants to have that particular strength. And that's very important because well, they're actually not really constants. They're slowly, somewhat dependent on the energy that you use. That's a detail. Basically, the energy dependence can be computed, but the integration constants and equations are basically three fundamental constants of nature that we do not know. We have to measure them. And the measurements give us numbers, and when you fill in the numbers, everything seems to fall into place. There's more coefficients, there's quite a few constants of nature here, which eventually are responsible for all the masses of the particles. Effectively, this means that also the masses of these fundamental particles cannot be computed because they depend on interaction parameters here and one parameter here that we don't know. And theory doesn't tell us what these numbers have to be, so we just go and listen carefully to our experimental colleagues who measure these quantities as accurately as they can and do an absolutely miraculous job of getting our numbers very accurately. But as theoreticians, we like to know where these numbers come from, and we don't know. We can guess, there are lots of guesses, and you all have heard of string theory to be one of the prime candidates of theory that should allow us to compute, to guess and compute these numbers, but they don't. So as far as we know, these numbers just come falling out of the air. Now, you can complain that this situation means that you don't understand anything in physics, but that's not fair. There has been a tremendous amount of work establishing this fact and all these details, both experimental, because theoreticians could not have guessed this without experimental input, and theoretically, because experimentalists would never have guessed this formula without theoretical input. So it's a collaboration of experiment and theory that together gave us this tremendous insight in how interactions work. But we don't know everything, and nobody should be surprised. Humanity has never been in a position that we could know everything. So there are still many questions to be asked. And of course, as a theoretician, I'm very much interested in these questions, and I would like to see if there are alleys that help us to understand the situation much, much better. And in order to answer such questions, we have to go to the domain of physics where all the mysteries are lying there open for us to inspect and to confront us with our complete ignorance. And yes, there are domains of physics where we're talking about. We often get letters from amateurs in physics who then say, well, that means you know nothing, and let me present you our theory, and I get theory of crackpots, basically, who then throw everything away and say, this is how it works. But that's not the way it goes in science. In science, we say, look, we have all this information, tremendously important. Don't forget that all this is known in very much detail. So whenever you come to theory, this already should be built in some way. And that's what makes it a little different. So the branch of physics where we now say we still know nothing is gravity. Well, again, that's not quite fair to say that. Because about gravity, we actually know a lot. And basically it all dates back from 100 years ago, maybe precisely 100 years ago, when Einstein presented his general theory of relativity. So let's call it GRT, general theory of relativity, that tells you that Einstein's relativity theory could be extended to include the gravitational force. It was a brilliant piece of intellectual work that took Einstein 10 years to get that understanding. When I was a student, I thought 10 years is an enormous amount of time for Einstein to think. When I'm growing older, I said 10 years is a really very short amount of time. That Einstein only needed to get this theory right. When you grow older, that's how you start thinking. Anyway, 10 years being a long time or a short time, it was what Einstein needed to get everything practically straightened up and to extend his relativity theory to include gravity. In a marvelous way, and you know what the result was. The result was that space and time have to be curved. And actually, when you look at the mathematics of GRT, which basically says that to this you have to add another term, L, and that's the Einstein-Hilbert action. Hilbert was a mathematician who actually also did a lot of work, partly independently from Einstein. And Hilbert realized that you can write general relativity exactly the same way. You just write here square root of G times types of the coefficient, and I could put here 1.85 G, sorry, 65 G, and then there would be the curvature of space and time. Space and time are curved, and R is a mathematical symbol indicating the curvature. Actually, only a small part of the curvature is called the curvature scalar. Curvature is a very complicated property of space and time, actually described by the Riemann tensor, which is a tensor which has 20 independent components. And this is only one of the 20 which happens to transform as a scalar on the Lorentz transformation. That's the only thing you can put in the action. And it was Hilbert who discovered that there's only one way you can write that action. It's like this, and then you add matter in such a way that it also works in curved space-time. We go into details, and I'll mention those details on as the lectures go on. This is just a generic introduction to my lectures. That this is again a very compactified way of phrasing the contents of the theory of general relativity. But there are two things which are very striking. A couple of things which are very striking. First of all, we're using the same kind of notation. We write also Lagrangian for gravity. And so at first sight it seems that it should be easy to put the whole thing together. To take this Lagrangian plus that Lagrangian and then say all that together describes the world as it is. There's one little thing, however, which was not yet included by Einstein. Einstein, as you know, was not very much in favor of the new theories of thinking that were also developing in this time, which is quantum mechanics. So this was a classical theory. In fact, this Lagrangian could also be considered from a classical point of view, that is, without h bar, and just looking at these equations as classical field equations. And you can understand this classical field equation as being in some limiting description to particles and particles interact very, very weakly as being the energy quanta of those fields. In Einstein's gravity, we completely ignore h bar. So h bar is 0, and then you get Einstein's theory, and it all works very beautifully. As you probably know, this general theory of relativity has been tested in great detail by experimentalists already in Einstein's time. Einstein knew that there was one experimentally observed experimental observation which did not agree with theory completely in his time, which was the slow motion of the perihelion of Mercury. Mercury is the planet closest to the Sun, the fastest moving planet at our Sun, and its orbit is not a perfect ellipse. Well, not orbits are perfect ellipses because they return each other, but the perturbation on the ellipse of Mercury did not quite follow the calculations that people were doing in those days, which were dictated by Newton's laws. So Mercury was slightly disobeying Newton's laws. And that was a piece of input Einstein realized had to do with the fact that Mercury is moving quite fast compared to the other planets. And moving so fast, it means that corrections due to which are proportional to some power of V over C, where V is the velocity and C is the speed of light. And those can actually be the biggest for Mercury. And noticing that Mercury was slightly deviating, Einstein immediately noticed that he had this theory that he could explain the anomaly in motion of matter. That was a first experimental result, but then there were many other experimental observations of a similar nature. The fact that light is deflected by the gravitational field is one, and later beautiful observations are made in binary pulsars, which also show deviations from classical Newtonian behavior, which you could measure and check with observations. And although gravitational waves have not yet been observed experimentally here on Earth, they have been observed indirectly in orbiting neutron stars, because neutron stars actually, when they orbit, they emit gravitational radiation. And by doing so, they lose energy in the orbital motion of these pulsars. This energy loss can be measured quite accurately these days, and it agrees with the Einstein theory of gravitational wave emission. So there have been beautiful confirmation also in Einstein's theory. So it is obvious to all physicists in the world that somehow we have to put these different theories together. And they don't just quite fit because Einstein had to assume the absence of quantum effects. If you try to introduce quantum effects in gravity, you're hitting a whole ocean full of difficulties. And the difficulties can be summarized. Well, one thing is that the particle associated with gravity is a so-called graviton. But it has spin 2. And spin 2 is not what we have here. So you say, well, what's the problem? Why didn't we have spin 2 right away? Why are there not more particles with spin 2 in the standard model? And later, people came with more extended theory, and it also has spin 1.5. The gravitino. And the gravitino comes about when you add what we call supersymmetry theory. In my lectures, I will not discuss supersymmetry, not because it would not be important. Supersymmetry has been a very well-studied branch of mathematical physics. But experimentally, there's less evidence for supersymmetry and supergravity, and also I don't need it directly in my considerations, which again doesn't mean that it isn't there. It means that for the time being, I don't see the need for introducing supersymmetry in your considerations, and I'll not discuss it. But I'm sure you'll have lectures about supersymmetry and supergravity as well. So that subject is certainly not to be ignored, but ignored in my lectures. So spin 2 and spin 3 halves cannot be introduced without being punished. The punishment is that it doesn't work very well with H bar in. And the reason is renormalization. So the notion of renormalization which is that one reason why mathematicians are usually not very much interested in this theory is they say it doesn't work. And it doesn't work because if you try to compute anything in this theory, you won't be able to understand how this particle interacts. You get meaningless answers, which means infinite answers. The computations do not properly converge. But being a physicist, being confronted with reality, that is to say, well, if you say it doesn't work, well, it does work in experiments. The experiment confirm this is the way things work. So if you say it doesn't work, that's just formalities don't work. We're just bureaucrats. Well, but the bureaucrats came to something important. They say we do a calculation. The calculation gives you infinite answers. What do you do? We discovered that you have to define your constants much more carefully than just plug them in your equation.